You've all done organic chemistry, and you've done the SN1 and the SN2 substitution mechanism. Now, in inorganic chemistry, things are unfortunately a little bit more complicated. We have 4 categories. And for the purposes of this lecture, we're only going to concentrate on substitution mechanisms and octahedral complexes. Okay? Now, basically, how this works, very similar to organic chemistry. As I said, we have 4 categories: associative substitution mechanisms, dissociative, and there's 2 furthermore called interchange A and interchange B. So there's 4 mechanisms for substitution in inorganic chemistry for complexes. And what you see here is a free energy profile of you've probably seen something similar in organic chemistry for an SN1 type substitution mechanism. And for the associative and the dissociative reaction mechanism, we essentially have an intermediate, right? And our intermediate is a minimum on a free energy surface. So we have 2 transition states and an intermediate. So that's the sort of the free energy profile for an associative or a dissociative process. Now, in contrast, if you look at an interchange mechanism, there is no real intermediate per se, or at least the intermediate, well, it's not an intermediate, it's essentially a transition state. It's a concerted substitution mechanism. So this, I guess, is similar to what you call SN2 in organic chemistry. Now, there's 2 types of interchange mechanisms that we have. We have an IA, which is sort of somehow resembling an associative mechanism, and an ID, which sort of resembles a dissociative mechanism. Now, the difference between an IA and an A, in other words, an interchange mechanism A and a formal associative mechanism, is simply the fact that we don't have a minimum on the free energy surface. That the process is concerted. It's a one-step substitution process. Whereas with A, it occurs in 2 steps, where you have an intermediate that you can perhaps detect spectroscopically, or even, if you like, isolate. It's difficult to do that, but it's in principle possible. Whereas here you basically have a very flat, well, it's a concerted process. Same with ID, right? So ID is an interchange mechanism that resembles a dissociative mechanism. And basically, both of these are concerted. So here we see it again. We have here on the left the reaction profile of a substitution reaction of some complex. Y is the incoming ligand. And we can clearly see that we have here, so this is an associative mechanism, and we can clearly see there a minimum on the free energy surface. So that minimum, if this is the complex, you can see the incoming ligand is Y, it's associating. This would be a dissociative process, and here we have the interchange mechanisms, and there are 2 types, IA and ID. All right, does everyone follow it so far? 4 mechanisms: associative, dissociative, IA, ID. A and D have intermediates, IA and ID don't. They're concerted one-step substitution mechanisms. All right. Now I want us to actually look at a little bit more closely at these mechanisms, and I want to look at the kinetics associated with them. All right. Now, very important is basically realizing that in order to do this, you need to remember something about kinetics, right, which you did in the 1000 course. So let's just review that. We've got a reaction, A plus B forms C, right? And there's a rate constant associated with that reaction. And we assume the reaction is first order in terms of A and B. What is the rate law for that? Can someone tell me?
It's the concentration of C over a concentration of A and B.
Rate?
Oh, it's A.
K, A, B. Remember that stuff? Right, so that's the rate law, assuming it's first order. If it was second order in A, it would be 2. If it were, yeah, so that would be a reaction that's second order in A and first order in B. Now, for the purposes of what we're going to discuss today, we're dealing only with first order reactions, okay, in terms of the substitution. Now, let's just write down what I've just said. We have an A mechanism and we have a D mechanism. In the middle, we have an IA and an ID. All right, so you can think of this as a continuum. On the one side, you have an associative mechanism where you actually have the incoming ligand associating with a complex, forming a transition state, and then going through, forming an intermediate, and then going through a transition state to form the products. That's the one side of the extreme. The other side of the extreme is D, where you have the ligand leaving, forming a stable intermediate, and then the ligand comes in a second step. And then in the middle, you've got IA and ID. So IA is these are the two concerted mechanisms, one-step mechanisms. And this resembles an associative mechanism in the sense that the rate of the ligand associating with a complex is higher than the rate of the ligand basically departing. And here, this sort of resembles a dissociative mechanism. So let's start with A. Let's have a look at A. So let's do this in the context of octahedral complexes. All right, so what do we have? This is what we have. We basically have a substitution. This is the overall reaction. Let's call this L1. That's the incoming ligand plus L. All right, so we want to look at this in terms of A, so an associative mechanism. So we can imagine that there's two steps. So this is an intermediate. All right, a formal intermediate, a minimum on the free energy surface. The incoming ligand associates with a complex, right? Let's call the forward reaction, give it a rate constant K, and the reverse reaction a rate constant K minus 1. Now in a second step, remember that free energy surface we looked at, that intermediate is going to essentially decay to form the complex ML5L1 and the ejected ligand. And and that will have a certain rate associated with it. Let's call the forward rate, give it a rate constant K2, and the reverse K minus 2. Right. Now we want to look at the kinetics associated with this. Now we make two approximations, right? The first approximation is called the steady state approximation. The steady state approximation. In German, it's called the Bodenstein approximation, after the scientists who discovered it. And this approximation says, simply, that the rate of change of the reactive intermediate is 0. In other words, it's being consumed as rapidly as it's being generated. Okay, that's the steady state approximation. It doesn't mean that the concentration is 0, it just means that the concentration with respect to time, the change in the concentration with respect to time is 0. So it's being consumed as rapidly as it's being produced. That's the first approximation. And the second approximation is we assume, because this is a reactive intermediate, that it's going to rapidly decay to the product, ML5L1, and that K minus 2, in other words, the reverse reaction, is going to have a rate constant of 0. So let's see what happens. I mean, if we put this all together. Now, if we employ the steady state approximation, the rate of change of this reactive intermediate over time is what? 0. Which basically means that it's being consumed as rapidly as it's being produced, or it's being produced, that there's no net change in concentration. So let's now take these two equations here and derive the rate law for an associative mechanism. Okay, so let's see how this works. What do? We say, okay, what is the rate of formation of the reactive intermediate? Well, from that top equation, assuming that it's first order in ML6 and L1, the rate of formation of this, or the production of this, is simply K ML6 times L1. So that's that reaction. That's the production of ML6. Okay. So let's write this down. Production of ML6L1 is given by that rate law. What about the consumption? What is the consumption given by? Connor.
Would it be K2ML5L1 plus L? Sorry, times L?
Sorry, say that again.
ML6L1 K minus 1.
Correct.
And K2.
Oh, yeah.
Exactly. So it's basically K minus 1, because that's consuming it, right? And at the same time, this would be another process that consumes it. So let's put those two together. So it's K2, these are rate constants, ML6L1 hash. All right, now, from the steady state approximation, we can actually equate these two together, because that's what the steady state approximation says. The rate of formation or production of the reactive intermediate equals the rate of consumption. So if we do that, what do we get? We get simply let's call this K1, sorry, this is K1. K1 ML6L1 equals K minus 1 ML6L1 plus K2 ML6L1. Okay. So what we can now do actually is we can make ML6L1 here, let's just factor this out. So if we take this out as a common factor, we're left with K minus 1 plus K2 equals K1 ML6L1. And basically, if we make ML6L1 the subject of the formula, we get simply ML6L1 equals K1 ML6L1 over K minus 1 plus K2. Now, those are actual constants, right? Now, that's an important result. And what we also know from the second step here, is that the rate of formation of the product, right, the product here, in other words, the change in the concentration of ML5L1 over time, which is after all the rates of formation of the product, we can write by the rate law ML6L1 times K2. Okay. And if we now substitute this expression here into this expression here, we get the overall rate law. So the rate is going to be K1 times K2. Just a moment. Yes, K1 times K2 times what we have there. So ML6L1 over K minus 1 plus K2. Alright, that's it. That's so that we've now derived the rate law for an associative reaction pathway. That's the rate law. Now notice, these are constants. They're just numbers. So I can actually rewrite this like this. Can't I? I just call it something else, K prime. The point is that that's actually the rate law for an associative reaction. And what this actually tells us, so this is the important result. What this tells us is that when a reaction follows an associative mechanism, the rate of the reaction is going to depend on what? It's going to depend on the concentration of ML6 and the concentration of the ligand. Both are going to affect the rate. Do you see that? You can clearly see that from the rate law that we've just derived. And that's an important result because it means that if you want to figure out if a reaction is associative or dissociative, you can play around with the concentrations of the starting complex and the ligand, and if there's a change in the rate, you can sort of say, well, it could be an A mechanism. So that's the story for an associative mechanism. You can play the same game. In fact, it's one of the homework exercises for a D mechanism, a dissociative mechanism, following the same derivation, the steady state approximation, and assuming that this reverse reaction in the second step is 0. You can do the same thing for a D mechanism, a dissociative mechanism, and what you end up with at the end is a equation that looks something like this. So for D, the rate law is given by K1, so following the same convention there, ML6, L1 over K minus 1L plus K2L1, and we have K2 there as well. So K1, K2, K minus 1. So you see the rate law is a little bit more complicated for a D mechanism. But what's very interesting here is if you look at this rate law, which you can derive in the same way, if the concentration of L were very, very high, what does that actually reduce to? Of L1, of the incoming ligand. So that's the generalized rate law for a dissociative mechanism. If I now if I look at this at an extremely high concentration of L1, what does this reduce to?
And the rate is going to be small.
Well, no. So think about it. This number becomes very, 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 very big. This number is very, very, very big. What's going to happen? Basically, this is going to become negligibly small, and everything is going to cancel, and you're going to be left with, this is going to be end up, because it's small, much smaller relative to that if the concentration is very high, and it will reduce simply to rate equals K1 ML6. You see that?
Does ML6 really matter? Because L is much bigger.
Well, that's the point. L1, the incoming ligand, has a much, much higher concentration. So basically, because it's so big, these terms this term becomes negligibly small, and because that becomes negligibly small, you can actually cancel stuff. So you just ignore that. The L1s cancel, and you end up with a rate law that shows what? What does it show? It's a first order reaction. That's right. First order.
It's a unimolecular reaction.
Unimolecular. Okay. Let's keep things simpler. Like, what does it mean? Yes, it just depends on the concentration of ML6. So it tells us that if you want to see if a reaction is following formally an A mechanism, do an experiment where you have an extremely high concentration of the incoming ligand, and then make it even higher. And if there's no appreciable change in the observed rate, the conclusion is that it's following a D mechanism. Because look, in the case of A, it does depend on L at all concentrations, right? So this rate law holds at all concentrations, low and high. So that's a way that you can experimentally distinguish the one mechanism from the other. So that's why understanding these rate laws and being able to derive them is important. Okay, is everyone following? Okay, so now that's the first thing. We have the rate laws, and we must be able to derive them. Now the next thing I want to discuss, the next very interesting thing I want to discuss, is the notion of, okay, we're scientists, and we have confronted with the substitution reaction, and we want to figure out if it follows an A mechanism or a D mechanism, we've only looked at those two extremes, or potentially an IA and ID. How do we distinguish that? Now, I'd like to say it's very difficult, actually, to distinguish a D from an ID and an A from an IA. Because remember, it's like a continuum. The difference is very subtle, right? It's just whether or not you can detect the intermediate long enough and, on the free energy surface. But there is another way that we can sort of experimentally extrapolate if the reaction is occurring via an A or a D mechanism. And the way that we do that is by, well, one of the ways is by evaluating three parameters. These three parameters. Delta V is called the volume of activation. Volume of activation. Delta S is the with hash is entropy of activation, and delta H is of course enthalpy of activation. Now, we can experimentally determine these values doing experiments. And what this really is, let's look at the situation. These are the two possibilities, or the two extremes. All right. So the top one is if we follow an associative mechanism. I've written there the intermediate. The bottom one is a D mechanism, a dissociative intermediate, plus L. Where in the first step, really, all that's happening is that the ligand is leaving, and you form this intermediate here, similar to an SN1 mechanism in inorganic chemistry. And so we've just looked at these two mechanisms and their rates and what they mean. This is A and this is D. Now, what these three parameters tell us is they look at the activated state, if you will. Okay? And let's start off with volume of activation. Now, the volume of activation you can think of is the size of the transition state bigger or smaller than the sum of the volumes of the two species that are reacting. Think about it. If you have an associative mechanism, it's like taking two balls and pressing them together, right? Because that's what happens in an associative mechanism. The incoming ligand associates with a complex and forms this thing here. So the volume of activation for an A mechanism will it be positive or negative? Negative. Negative. Because it's like squeezing two balls together. Here's a ball, it's the complex. Here's another ball, it's the ligand. Fuse them together like plasticine. You have a compressed activated state. And it follows, therefore, that the D mechanism you will have, because you're dissociating a ligand, the volume of activation increases. So this delta V here will be of activation. For that reaction will be negative, and for this reaction will be positive. Now we're looking at A and D, the two extreme cases. What about entropy of activation? Who wants to venture a guess?
Well, the entropy is defined as a logarithm of the amount of states possible.
Okay, well, that's a complicated. You're a physical chemist, but yeah. Okay, fair enough. Go on.
In the case for an A, I would say it decreases, and for the D case, I would say it increases.
Correct. Very good. Because it's like if you put things together, the amount of disorder decreases, right? So that's what we're doing here. We're putting stuff together, so the amount of disorder is going to decrease. Exactly. And following the same line of reasoning without microstates, the D mechanism will be positive. Now, you can evaluate experimentally the delta V and the delta S value from something called the Eyring equation. And this equation relates, this is an important equation, the rate, so that's the rate constant rather, K, of a substitution reaction can be written like this. Alright, that's the Eyring equation, also called the Eyring-Polanyi equation. And it relates the rate constant, K subscript B here is the Boltzmann constant, H is Planck's constant, and delta G here is free energy. So that relates, in fact, the free energy of activation, to the rate constant. So this equation gives us essentially the enthalpy of activation, which incidentally is another parameter that doesn't tell you too much, right? The important parameters are delta V and delta S. Those are indicators of whether a reaction is following an A or a D or an IA or an ID mechanism. You can also determine, so from this equation you can determine delta H and delta S of activation. Okay? We'll look at that in a minute. Now the volume of activation is another parameter. And the volume of activation, you see, this is exactly why I don't like using this thing, because the volume of activation is defined in a different way, but we can also determine it experimentally. Okay. So this equation here is how we get the delta H and the delta S of activation for a reaction. We do it experimentally, and here we can actually see what these terms mean. So from the Eyring equation, if I rewrite it, right, because it's written in terms of delta G here, I can rewrite that in terms of Gibbs free energy and rearrange this equation, and I basically get this thing here, right? I've just basically taken the logarithm, the natural log, and rewritten it. It's basically a rewritten form of the Eyring equation. This over here is the definition of the volume of activation, right? And it is defined as essentially the response of the rate constant with respect to a change in pressure. In other words, if you change the pressure of a reaction, a substitution reaction, and look at the change in the rate constant, or the logarithm of the rate constant, you can determine the volume of activation. And if it's negative, as we saw here, it's going to follow this. So it suggests it's associative, and if it's positive, it suggests it's dissociative. Right, so these are important things. Now, coming back to the Eyring equation, or the way that I've rewritten it here, which is essentially a masked form of the Eyring equation, or the Eyring-Polanyi equation, if we plot K over T, in other words, the rate constant over T against the reciprocal temperature, we'll end up with a straight line. This is kinetics, right? You probably did some of this in the 1000 course, or you should have, right? Similar stuff. Now, incidentally, this comes from the Arrhenius equation, very similar to the Arrhenius equation. Point is, the take-home message is if you plot it, for example, here we have an example where at different temperatures we've determined the rate constants of a substitution reaction, and you end up with what we see there. And essentially the intercept, the y-intercept, is simply the log of K over H. So you can actually, from this data, you can actually determine the delta S value from the intercept, and the delta H value is essentially reflected in the slope. The slope is minus delta H over R, where delta H is the enthalpy of activation. So you get from minus delta H over R, the slope, you get the enthalpy of activation, and from the y-intercept there, you get, as you can see here, the entropy of activation. You can actually determine these values experimentally. Now, here we have some actual values. Let's look at the first start at the bottom here. So what these people have done is they've actually done these experiments and determined the volume of activation for the substitution reaction In other words, of this series here, so cobalt, rhodium, chromium, all 3+ oxidation state. So we have a penta-amino complex with one water, and we're exchanging it out with an isotope, water that's labeled, right? So, yeah, there you have it counts for triradicals. So, what are we doing? We're basically just exchanging this water molecule here, right? Does everyone see that? Okay. Now, what do you see? What do you see? What do you see happening there? Let's start with cobalt plus. What does that tell us? It suggests exactly it might be dissociative, or, in fact, more likely is that it's interchange dissociative, ID. You see, it's a continuum. It's very difficult from this data to draw a line between when it's formally D and ID. You can't really say. But if it's positive, it certainly is either D or ID. Okay? Remember, it's a continuum. A, IA, ID, D. Right? These are negative. Right? Let's look at the rhodium, minus 4.1. What does that suggest?
Suggestion lies more in the associative side.
Correct, correct. It suggests it lies more in the associative pathway. So it could be A, or it could be what? IA, right. Difficult to say. The more negative, the more likely it is it's moving to a formal A mechanism. So it's kind of difficult to draw the line, right? It's difficult to dissociate because the difference is actually subtle. The only difference really between an I and an IA and an A mechanism, or an ID and a D mechanism, is really, the energy of that intermediate, if it's really a negative or a minimum of the free energy surface. So anyway, you get the picture. Point is, you can experimentally, and you can play the same game with delta S, right? So you can determine, as I've shown here, experimentally, the entropy of activation, and following the same reasoning, if you determine delta V and delta S of activation, you can basically, in no time at all, sort of make assessments as to whether the reaction is A or D. All right, so let's just summarize what we've discussed up until now. We've looked at the four mechanisms. We've looked at the rate law governing A, the rate law governing D. We've looked at parameters that indicate whether it might be, what sort of mechanism it's following, particularly delta V, volume of activation, and delta S, entropy of activation. And in addition, we've also seen from the derivation of the rate law that in a D mechanism, formal D mechanism, it's or formal A mechanism, it depends on the concentration of the ligand and the complex. And in a D mechanism, at high concentrations of the ligand, it only depends on the concentration of the starting complex. You can infer that from the rate laws. There's one further point I want to make. So when you're studying this stuff and you want to figure out the mechanisms, another thing you can do is, for example, and it sort of seems reasonable, you can change the identity of the incoming ligand. So let's say you have a substitution reaction and you suspect the mechanism is associative. And let's, for argument's sake, say it's, let's just do it over here. Let's say for argument's sake it is something like this. Well, let's take what we just saw. Let's say NH3 5 H2O. Yeah, something like that. There's a complex, a generic complex with some charge. Doesn't matter. And I think that it is, I suspect it might be following associative substitution mechanism. So let's say I substitute this with NH3, which is isotope labeled. The product is going to be NH3,5NH3 with some sort of isotope label, plus H2O. That's a substitution. And I'm saying that substitution follows perhaps an associative mechanism. How can I prove that? Well, I can do the kinetics we looked at. I can change the concentration of the ligand, in this case ammonia, and if I see a response, if I see a dramatic response in the rate change, I know that it's probably following from the rate law an A mechanism. If not, it might be following D. What else can I do?
Try and isolate the intermediate.
Try and isolate the intermediate. Yeah, that's possible, but very, very difficult. And probably not going to work. Probably not going to work. What else can I do?
Can you look at the experimental values for the parameters?
Yes, we can look at delta S and delta H and delta V, and based on that, if it's negative or positive, draw a conclusion. What else can we do? Well, if it's associative, and I change, let's say, and I do one experiment where I use ammonia, and another experiment where I'd say take trimethylamine, right? And another experiment where I take triethylamine and so on. If the reaction is associative, will there or will there not be a change in the rate constants of those experiments? There will be a change. Sorry, not the rate constant in the rate. Because it's associative. So associative reactions depend also on the identity of the incoming ligand and its relative nucleophilicity. So if the reaction happens to follow a D mechanism, we saw from the derived rate law, it's can sort of infer that, but if it follows a D mechanism, the rate determining step has nothing to do with the identity of the incoming ligand. The rate determining step is essentially the cleavage of the ligand that's being replaced. And you can change the ligand as much as you like, it's not going to affect the rate that much. And then the inference is that the reaction is following probably a D mechanism. Okay? All right, so those are important things. Now, the next thing I want to look at in the context of substitution mechanisms, and this is very important, is the concept of something called the Eigen-Wilkins mechanism. Okay. Now, this is a mechanism that's important, very important, in explaining and rationalizing the substitution of octahedral complexes. Okay? Octahedral complexes. And it comes from a guy, well, two guys, Manfred Eigen and Wilkins, and they did this work, I guess, in the 1930s or 40s. And what they were trying to do is basically explain the substitution of water in octahedral complexes. Now, you can think of the Eigen-Wilkins mechanism actually as a mechanistic rationale of the interchange mechanism, which we've not looked at. We've looked at A and we've looked at D. But it turns out that the substitution of water molecules in octahedral complexes generally, in fact, follows an I mechanism, IA or ID, interchange. And so the rate laws we derived earlier that we've been discussing, you cannot really employ. So you have to turn to the Eigen-Wilkins mechanism, which is a special mechanism for interchange, for the interchange mechanism, particularly for octahedral complexes, right? But it's kind of general. Okay. Now how this works is, well, before I get to the actual mechanistic details, I just want to show you, and I find this quite remarkable. Here we have a table of water exchange rates. In other words, if we imagine taking complexes or metals with water molecules coordinated to them, and we exchange those, look at this enormous range of rate constants, 16 orders of magnitude. Some of them are what we call labile, meaning that they react very fast, right, kinetically, and some are inert. So, for example, these are inert, and these are extremely labile. Look at that rate constant there. Look at that. So you can draw some important trends from the stability with respect to substitution. All right, and some of those points. This comes out of the textbook. By the way, this lecture and the one to follow is not based in Alschenborg. This you can follow the textbook from the last semester. They have some good explanations. But basically, you can draw some trends. I'm not going to go into those now, but essentially the idea is that you have some complexes that are substitutionally labile and some that are substitutionally inert, and there are electronic reasons for this. And one of the most important reasons is if you have, for example, an octahedral complex that has electrons in the Eg orbital. Let's actually just look at that, the notion of lability. I think it's important. So we've got this notion of labile and inert. Labile means it reacts quickly in terms of substitution. Inert means it reacts slowly. Inert, 10 to the minus 6. Labile, 10 to the 10. Wow, 16 orders of magnitude. Now, let's take two examples. Let's take these complexes here. OH2, OH2, OH2. So hexa-aqua complexes. And we're interested in studying the lability or the inertness of these complexes with respect to substitution with some other ligand, okay? Whatever charge it has. Now, they're octahedral complexes, so we can fortunately use what? We can use simple crystal field theory to rationalize things, okay? And this is, I think, one of the most important ideas that explains lability or inertness of octahedral complexes. Let's suppose we've got two possibilities. Two complexes. One has the following electron configuration, and another, let's say for argument's sake, has the following electron configuration. Which of those two complexes do you think would be more labile? In other words, which would react more quickly to exchange ligands, and why? Why? Okay, because it's an unpaired electron. Yes. Not entirely correct, but you're on the right track. What? Where's that unpaired electron? In? Eg. What is Eg? Yes, yes. It's orbitals that have antibonding characters. So if I'm putting electrons in an antibonding orbital, it's going to do what? It's going to essentially weaken the strength, if you will. This is a very simple way of looking at it, of the metal oxygen bonds. And it's going to result in a complex that's more labile. Very simple. So this would be more, a configuration like this would be more labile. So that's one way of, there are other things that one has to take into consideration, but essentially that's one way of rationalizing this. Also looking at the crystal field splitting parameter and all sorts of other things. Basically it comes down to the electron configuration. You can see, for example, here we have ruthenium-2, which is very inert, and we go across, there's iron-2, much more labile. Right, and this is for a series of complexes of this type. Right? Studying the substitution. And so water is much more labile compared to ruthenium. Why? Why? Iron 2 plus compared to ruthenium 2 plus. Why? Because of the crystal field splitting parameter. With ruthenium, it's much bigger. So it's going to be T2G6. That will definitely be the electron configuration, remember? Based on crystal field splitting parameter. And for iron 2 plus, there might be, certainly in the hexa-aqua complex, it will, the crystal field splitting parameter will be much smaller, and you'll be populating the Eg, the antibonding orbital, and that explains why it reacts much faster. Look at that, several orders of magnitude. So you see, that's sort of the idea of inert and labile. I want you to be comfortable with that. Now let's come back to the Eigen-Wilkins mechanism. So basically, the Eigen-Wilkins mechanism, as I said, is a mechanism that explains or rationalizes substitution in octahedral complexes, particularly aqua complexes, and it follows the inert, which generally follow, the interchange mechanism. I'm talking such rubbish this morning. Generally follows the interchange mechanism. All right. Now, so Eigen-Wilkins mechanism. Okay. Now, how this mechanism actually works is essentially you take an aqua complex, for example, something like that. You have an incoming ligand, let's call it L, and you generate something called an encounter complex. Now, the way to think about this encounter complex is that it is essentially the incoming ligand diffuses towards the complex. They come into contact with each other pretty much like what you would think of in an interchange mechanism. It is essentially really the interchange. It's sort of an interchange type intermediate. And then so this is a pretty slow process. This is slow. And then what happens is once that thing is formed, you go to the product fast. Sorry, so this would be 5L plus H2O, so substitution. And, sorry, it's the other way around. This is, yeah, overall that process is slow, yeah. I mean, you can actually break this down into 2 steps, but let's just keep it like that. And this is called an encounter complex. Now, one can show by using kinetic arguments that the rate associated with the degradation of the starting material following an Eigen-Wilkins mechanism is given by this equation. Concentration of M you can very easily actually derive that from kinetic discussions.
What is?
Just I'll define that in a moment. Just a second. Let me just rewrite this because it looks terrible. Okay. What is Ke? Good question. Ke is what we call the pre-equilibrium constant. It's capital Ke, pre-equilibrium constant. Because remember, in the Eigen-Wilkins mechanism, which is a mechanism for an interchange reaction, that thing over there is not really an intermediate. That's why we call it an encounter complex. And the pre-equilibrium constant is nothing more than simply this equilibrium. So the concentration of the encounter complex over the concentration of H2O6 times the concentration of L. That is essentially what that is. So the question now is, right, so this is now a whole different kettle of fish, how can we actually, how can we experimentally determine this free equilibrium constant? Because apparently we need it to get the rate of the reaction. All right. This is the pre-equilibrium constant. This is the pre-equilibrium constant. KL is a rate constant, small k. Now the question is, how do we do that? Well, we can't do it experimentally, unfortunately. But what we can do is we can evaluate the KE value. The pre-equilibrium constant can be found numerically by something called the Eigen-Foss equation. Now this equation, I don't expect you to memorize the equation, but the equation is a way that we can evaluate the KE value, and it's given by the following formula. Don't need to, of course, know this. All right. So what that equation is, it's really a relationship between n is the Avogadro constant, pi and all these other constants. V is the electrostatic potential between the two, in this case, for example, the complex and the ligand, well, between the complex and the ligand. And A here is the distance of closest approach between the starting material or the complex and the incoming ligand, right? So what does that equation tell us? Let's look at that equation. If I have a big ligand that's coming in, a big ligand, big, will that drive the K, will that make the pre-equilibrium constant big or small? Big, yes, because A cubed, A is the distance. Remember, you have this encounter complex. So the distance between, let's say, the metal and the ligand, that's A. So if the ligand gets bigger, Ke gets bigger. And what's the consequence of that? If we look at the rate law of the Eigen-Wilkins mechanism, if Ke is increased, here it is. If Ke is increased in size, what is the consequence for the overall rate? If Ke goes up,
You can cancel it.
if it goes up, so let's say we've got two experiments. The one we take ammonia, and the other one we take trimethylamine, right? And we use the Eigen-Foss equation to evaluate the Ke, which will have a bigger Ke value. Trimethylamine or ammonia? Yes, because it's bigger, exactly. And which will have a larger rate constant? Which will have have a faster rate? Yes. Because if K, look at the equation. If you increase K, right, proportionally, overall the consequence is that you increase the rate constant, basically. Now the other thing that the Eigen-Foss equation has is V, this electrostatic potential between the two species, and that depends on the charge and stuff like that. So there's two things that the Eigen-Foss equation takes into consideration: the size, in other words, the distance of closest approach between the ligand and the metal, and the electrostatic potential. In other words, if they have opposite charges, that's also going to increase the value of the pre-equilibrium constant considerably, right? Because you can see that V is, it's also called the Debye-Huckel potential, will be increased. And so you can evaluate the Ke value numerically, and you can then use the Eigen-Wilkins equation to actually determine the rate of the reaction. And this equation, as I said, follows most octahedral complexes, follow the Eigen-Wilkins mechanism of substitution. It is, per definition, an interchange mechanism, as you can clearly see from the formulation of this encounter complex. But it's a special, you can think of it as a special type of interchange reaction, essentially. And yeah, so I think that's the end of that for now. So are there any questions?
Can you experimentally determine V, the electrostatic potential?
No, but you can calculate it very simply because it's an equation that you calculate it's Z1, Z2, E, to the permittivity of space with a 4 power cubed,
The Coulomb
that
equation.
equation. So you don't even need to determine experimentally. You can just actually plug in the values, essentially, because it's the charge. It's the charges of the complexes. Anything else?
Why do we neglect enthalpy when we look at the 3 parameters?
Yeah.
Why don't we look at the enthalpy?
You can look at the enthalpy. In fact, it turns out that the enthalpy will be positive. I just don't, I think this lecture was already so overloaded. I didn't want to discuss it, but yes, you can look at the enthalpy of activation, sure. And it turns out that if it's positive, then it's, let me just think about it. If it's a negative volume of activation, it's associative. And if it's positive, it's associative. So if delta H is positive, it's associative. If delta H is negative, it's dissociative. Or, remember, interchange. You can't really distinguish easily from those parameters whether it's D or ID. Right. So it's really, it's kinetics, right? It's absolute kinetics. So what I expect you to be able to do, well, we'll discuss that later in the tutorial, and I think a lot of the questions that actually come up in the first tutorial we've already really discussed in class. But anyway, we will discuss this later. So let's have a break, 10 minutes.